last problem, number 24, was that our function was z equals f of xy equals x squared minus y squared. Graph is called a hyperbolic paraboloid. It looks like a saddle, like a horse's saddle that you're sitting on. And we are parameterizing it over a circular disk of radius 1 centered at the origin. Not just the unit circle itself, but everything inside the unit circle as well. That is the region we're parameterizing over. Therefore, the way I taught you to do it is you'd want to let R of uv be a vector, a three-dimensional vector, whose first and second components are effectively polar coordinates. Yeah, we can actually do actual polar coordinates in this case. V cos u, V sine u. By the way, the roles of u and v could be swapped. We could do u cos v and u sine v. By doing it this way, I'm just being a little bit more consistent with the way the book does it. Effectively, u is an angle from 0 to 2 pi. And v is the radius from 0 to 1 when you do it this way. If it had been the disk of radius 2, we also ended up multiplying by 2 in there. That's only done so that v can still go from 0 to 1. But you actually don't have to multiply by 2. Instead, you could just let v go from 0 to 2 and use a very similar parameterization. If that was confusing to you, you have flexibility in these things. You can do it in more than one way. But here, since it's a disk of radius 1, v is effectively the r polar coordinate. You also could use r and theta instead of v and u, if you prefer. Then you also plug these things into f, v cos u in place of x, v sine u in place of y, and get your vector. Okay. We are going to need Mathematica to help us do the calculations again. So I will define my function f of xy, x squared minus y squared. I will define my vector r of uv. And again, I really didn't make use of the curly braces in what I showed you so far, but I have in mind a certain way to use them, probably not till next Monday. So I'm going to consistently use curly braces here for the input even. Again, v times cos u, comma v times sine u. Then plug those same things into f. You could copy and paste if you like for saving time. F of those things. And we could simplify, see what the formula looks like. Expand seems to work best. There's what the formula for the parameterization looks like. If you want to see it, parametric plot 3D is what to use. As u varies from 0 to 2 pi, getting the limits of integration right is essential, and v goes from 0 to 1. And it's part of the paraboloid. Looks like it's a plane. It should not be a plane. Where? Oh, here? Okay, thank you. There's the formula, and okay, yes. So it's part of the graph that looks like a saddle. We're interested in the surface area of this, the technique from this point on is to create a vector of derivatives, r with respect to u, and then r with respect to v, r sub u and r sub v when written by hand. What's it doing there? I think it's because I forgot the curly braces. That's doing it. Okay, I actually don't want to make that vector, that as a vector. I want to calculate those things separately. Sorry. There's r sub u. Here's r sub v. These are the two things I want to take the cross product of. Remember, what we're ultimately after here is the thing that's labeled ds, small element of surface area, is the magnitude of the cross product of these derivatives, dA. It's very analogous, by the way, to, it's analogous to d little s equals magnitude of r prime of t dt for parametric curves. Very much analogous to that, actually. I mean, if you wanted more detail here, you could also use the fact that the magnitude of a cross product is the magnitude of the first vector times the magnitude of the second vector times the absolute value of the sine of the angle between them. So it is analogous to, it's proportional, you might say, to the magnitudes of these derivatives. And they could be thought of as velocity vectors in, say, like a u direction and a v direction. Separate velocity vectors, though the angle between them affects how much areas get expanded. When the angle is small, these vectors are close together, small angle. Sine of the angle is small, they don't affect areas as much. When they're perpendicular, angle is 90 degrees, the sine of 90 degrees is 1. Small changes in u and v have bigger effects on the areas, is the intuition. Not doing proofs, I'm just trying to get intuition into your head, how to think about these things. It is kind of analogous to that. Not the exact same thing, obviously. So we do need to form the cross product. Anybody look up Christopher Cross? Crisscross. I should show you. Have you heard I think it's the song is called Sailing. Sailing. Okay, that's like a 50-year-old song. Is Crisscross's most famous song. Did you check them out? All right. There's the cross product. Taking the square root of that cross product of it dotted with itself is the thing that needs to get integrated. And maybe expand will simplify it. Maybe not. Maybe simplify. Okay, that one simplifies fairly nicely. Amazingly. And so the integral to do to get the right answer, which we probably could do symbolically here. We could probably do the integral from 0 to 2 pi, integral from 0 to 1 of this thing, dv du, u goes from 0 to 2 pi, v goes from 0 to 1. It gives an exact answer. That is approximately what I told you the answer was. You also can use n integrate instead, which is right off the bat just going to give you a numerical approximation. Here's the syntax. Same thing. Okay, but looking at Dr. Yang's key, he didn't do it the way the book did. He did something that turned out a lot simpler. He just said, instead of parameterizing like this, why not parameterize like this? Use x and y instead of u and v as your parameter, but use the disk as your region of integration instead of a rectangle. And how about use polar coordinates for the disk? You can even do the calculations by hand. What is f of xy? That's x squared minus y squared. Treat the x and y like the u and the v. Rx, derivative with respect to x, is going to be 1, 0, 2x, pretty simple. Ry is going to be the derivative with respect to y, 0, 1, negative 2y, pretty simple. Calculate the cross product of Rx and Ry, which I'm going to do I forget the formula offhand. I need to remember it with a determinant that I write like this. Just trying to do it as quick as I can. Okay, just if you're not sure what I'm doing, just ignore it. I'm just trying to get the right answer for the cross product by hand here. I'm trying to do it in my head as quick as I can. looks like it's gonna be negative 2x, positive 2y, 1, if I did not make a mistake. And the magnitude of that is the square root of this thing dotted with itself. That'll be the square root of 4x squared plus 4y squared plus 1. And effectively, that's the thing to integrate over the disk here, call the disk D, dA, and then we could do that with polar coordinates. It's actually not too hard. Replace the x squared plus y squared with r squared, and replace dA with r d theta. Theta goes from 0 to 2 pi, r goes from 0 to 1. So the limits of integration after conversion to polar coordinates are the same as what we did with u and v, because u and v were effectively polar coordinates. But then the integrand becomes square root of 1 plus 4r squared r d theta. It's a different integral, though effectively equivalent to the other one, though it's not obvious. And you can do this integral not too bad by hand by doing a substitution. U equals 1 plus 4r squared. Du is 8r dr, etc. It's not too much different than the integral that way Mathematica actually did. Yeah, it's effectively the same, though it's not obvious about why. Because in this square root, you could factor out a v squared. And then the square root of v squared is the absolute value of v. And then the absolute value of v when v is positive is equal to v. And you effectively get this integral here. You effectively do get the same integral. Just a simpler calculation as far as this stuff goes, compared to doing all that. Imagine doing that by hand. With ultimately a simpler parameterization and simpler derivatives and simpler cross products. And that thing looks simpler at first, and you don't have to do lots of stuff with trig functions. But just do it over the disk instead of the rectangle. Though in the end, you're really doing it over a rectangle and say an r theta pun in the end. It really ends up being equivalent.